Okay, cool. Are we behind and how much time do I have before I start?
You can start whenever you're ready.
Okay. I didn't know what our cutoff time is. It's like 4:30 for you guys, right?
You were the last talk, so you can go until we're like throwing tomatoes at the screen, which that's probably not going to happen. So,
Okay. Okay. So I'll introduce myself. I guess I'll start there. And then I'll just say that I put together a few slides here with not a lot of context, maybe. So people should ask questions, but also I'm happy to like chat offline and provide more. So anyway, my name is Cassie Lumbrazo. I'm working at the University of Alaska. I'm currently in Juneau right now. You guys are talking a lot about the Juneau ice field, I think. I am here. It is dumping snow. It's kind of crazy. Uh, yeah, I've been doing a lot of field work in the past week here and related to this work I'm presenting on. Uh, and really, I'm a postdoc working on modeling the snowpack around Juneau using the snowpack model. So confusing, lots of snowpack being thrown around. And I'm just going to show a little bit of what's going into that today and kind of, yeah, just talk about what our plans are for the ice field but really just an overview. So I'll get started. Let's see. Yeah, some of this is just super high level, but like I'm just sharing some of the sites that we're looking at. You guys are probably familiar with the area, but these are three sites around Juneau that we're doing some modeling at right now. Powder Patch Met Station, which is like on Douglas Island. There's the tram, which is like just off the ice field, and then there's Hien Latin Snowtel, which is just like up a bit higher in elevation on the mainland side. So these are three of the sites that we are currently modeling on. And then, of course, there's also the ice field. But this is where we have continuous snow depth observations. So these three sites, we have like 10 years or more of snow depth from sensors at met stations. With those stations have temperature, precipitation, not always precipitation, but temperature, relative humidity, and some other observations depending on the station. The point is that in order to do snow modeling, we really need validation data. This is a few sites that we have continuous snow depth validation data. So for example, we're doing some modeling going back to like water year 2024, 25 to do some validation and setup. And then I'm also going to be modeling to 2026 and maybe on the ice field from 2024. So we'll talk about that. This is just cool to see. This is all of those years, for example, at Powder Patch, which is on Douglas Island, put on top of each other by water year. And it's just cool to see the snow depth variability, the seasonal snow depth variability over the area. There's a lot of variability in the timing of snow melt and then large scale, the just amount of snow that there is in the area. And this is even more pronounced on the mainland as well. So this is just on the island on Douglas. And of course, this is seasonal snowpack. So this is all seasonal snowpack sitting on top of the soil, for example, for these sites since they're off the ice field. And then this is just a few points, nice, very low resolution plot you have here. But this is just showing in context of where these sites are that I'm looking at. So like Hien Latin and Mount Roberts Tram and the Powder Patch, this is where those lower elevation sites are. And then there's, you go up on the ice field and I have in parentheses here, like modeling at the GIF TKG4 site, for example, because we're kind of trying to identify right now locations on the ice field that could be ideal for modeling, for example. And really, you'll see why there could be complexities with that. But this is kind of the spatial orientation of our modeling sites down here in blue with the ice field and maybe some modeling on the ice field to come. We're using the snowpack model, which is a physically based snow model. I don't know if people are familiar with it. I will do super high level, but the model was developed by SLF in Davos, Switzerland, a group there. And basically it's a physically based snow model that really has all these parameterizations for the mass and energy exchange of the snowpack to the atmosphere, and also the snowpack to the ground below. So that's a pretty key component depending on where you're modeling. But the snowpack model actually describes all of the snow microstructure. It's very high resolution development for what's happening in the snowpack itself. This is extremely valuable for if you're trying to model the snowpack in complex regions that have a lot of variability in meteorological conditions that affect the snowpack, and if you're trying to model for avalanches, which actually there's kind of some dual interest for this modeling work in Juneau for avalanche related work and also for hydrology. So it's very multi-purpose kind of application, but this is some of the physics that's involved, and I won't go into all of it, but the point is that you can basically get snow profiles of the snowpack at any point in time when you model over a season, and I'll show some examples. And yeah, you need a lot of input data to do this type of modeling. So you need, all your inputs, solar radiation, and your long wave, short wave, temperature, even ideally like surface temperature and other things to do this type of modeling. But you can do it with a minimum set of forcing. This is kind of like a horrendous diagram, but just showing like what my current setup is that I'm working on is just, we have like some forcing data sources and different variables that we're doing different downscaling for, depending on the resolution of the scale that we're going for. But in short is that like over here on the left is that I'm currently working on this little iteration, which is like we're doing some point simulations and we want to do like detailed model evaluation and validation using snow depth, snow density, snow temperature, stratigraphy, liquid water content, and even down to like grain hardness type and size, which this can really then tell us how our model's doing at these points where we have a lot of data. So then we can like scale it up and go to places where we don't have as much data, for example, for an entire year. So this is like over here on the left is like where I'm really iterating. And then over on the right is like we're doing some work to get there, but we're not quite there in some spatial resolution. There's a lot of forcing data requirements for this type of model, of course, which kind of ignore on the left. This is leftover. Sorry, I should have cleaned that up. But on the right, we have, some like we're using her atmospheric model data, which is gridded at 3 kilometers resolution that we can then do some downscaling for. And for the model forcing, it's really like all of these variables here on the right. Usually local met stations don't have all these variables. You end up with just temperature and precipitation. Maybe you have relative humidity or precip, or in snow depth, but really then you have to go for a physically based model that requires a lot of input. We have to go to this like larger grid scale for an atmospheric model to force it. And then model evaluation and validation, from stations, we can have snow depth and SWE often. If you have a SNOTEL, or if you guys are taking, snow, like liquid water or SWE measurements on the ice field, but we also could use, any like snow profiles to then get snow stratigraphy, liquid water content, layer hardness. And there's a lot of other ways to get those validation data, but and some of this can be, like I said, station data, which are like these little points, and then you can have some gridded atmospheric data, which we can do downscaling for and basically do modeling. So anyway, won't go into the details of all of it, but that's like the general workflow of what we're going for. We are using currently her AK atmospheric model forcing data at 3 kilometers resolution. And this is like an example of zoomed into at 3K to the Juneau area. So this is like, this point would be on the ice field up here. And then you can see kind of the outline of Douglas and Heen Latine in the tram. So that you basically just have these 3 kilometer grid cells, and you can stack that over time and pull grid cells to get single time series of your forcing data. And I did a lot of work to compare her atmospheric model forcing data time series to station data. So I have I'm not going to show any of that, but if anyone's curious, I've done a lot of comparisons to see how the forcing data is doing and how much downscaling we need to do. So that was a huge part of the work that I won't show. But for example, like one of the downscaling can be like when we're doing spatial work is doing downscaling with Wind Ninja, if anyone's ever heard of it, but it's for downscaling wind fields. If you want to get down from 3 kilometers resolution, you can use like some DEMs, downscale, and get down to 100K, 100 meters, not 100K, 100 meters. And this is a downscaled image of wind speed, for example, over Douglas Island. And you can, pull this grid cell where we have some wind data and compare. So this is kind of the work I was doing to prepare some forcing data for distributed simulations and also validation for point simulations. This is kind of just cool to see a visual. So like here's Douglas, like on top right, you can see that this is like one square over Douglas Islands outside of Juneau. And this is like, this larger image is like facing west if you're like at the Eagle Crest Resort, if anyone's ever been up there. I was there this weekend. It was really nice. And this is wind speed and direction, for example, at 1,000 meters, 500 meters, and then down to 100 meters. So you can really get this like resolution of refining topography and getting some better wind speed from atmospheric model data instead of having, a lot of our wind speed sensors in this region get super rhymed, and unless they're like heated, maintained, and monitored, the wind speed can be pretty rough from observation. So this is one way. There's been a lot of research comparing this downscaling scheme to anemometers that are out in the field. But yeah, so this is kind of a cool little visual of that. So in general, my point is that all this is like kind of over here now. That's comparing the, some downscaling wind speed and dealing with forcing data. But we also need to do model like validation, and evaluation. So we really need some like observations also. So if we do all this modeling, it's like, well, then what does that look like? And this is an example output of snowpack. For example, you have this time series of a simulated snowpack with grain shape, and you can take one point in time here, that dotted line, the dashed line, and you can get a snow profile for a modeled simulation. So basically, one thing we can do is we can like dig snow pits. This is an example of a powder patch. Some pretty tall snow pits, we can dig snow pits and get this information to then do model validation. And so that's one of the things we are currently working on out like in Juneau and on Douglas Island. And this is an example snow pit, for example, but the point is just that this is some real data that we collected last year. This year, we were just up there last weekend and we dug a pit that was 3 meters. It was quite deep up there, so it was a lot of work, but this type of data is very useful. This is temperature, a temperature gradient in the snowpack, and then you can see some layering and some melt freeze crust and some new snow and rounds at the bottom. So, and this is snow density we can use for model validation as well, we can validate snow density. So this is all model validation data that we've collected in the area. And I know that there's some snow pits maybe being dug also on the ice field. So this can be like validation data for snow modeling. And an example of a modeled simulation over Juneau. So this is at Powder Patch. This is just example. In black is observations. And in blue, we're modeling with just atmospheric model data. So just the Hurricane with a little bit of downscaling. And then in green is the METS, using as much data from the MET station that we have, and then filling the rest with her data. So this one interesting thing to look at here is that her atmospheric data actually does quite well at reproducing the general trends of the snowpack accumulation. But when it comes to snow ablation in the melt out season, when we're using MET station data, that's really tracking much closer in the timing and the amount of snow melt. So there's no like final result to be said here right now, but the point is that we need to consider our forcing data when we're doing modeling, and it's the most important piece of modeling. Otherwise, if you put in a bunch of terrible data, you're going to get a terrible output, and then it's not the most useful. So it's important to do this level of like sensitivity tests and comparing with station data that we have. And this is just quite preliminary, but it's interesting to see that there are some differences depending on what forcing data you're using, of course. And I could hypothesize all day potentially why there's these differences, and we can talk about it offline, but I won't go into it at the moment. Some output example simulation. So one of those modeled lines, this is an example of that modeled line. And this is liquid water content in the snowpack. So this is snow height up to 2 meters and over water year 2025. So this is an actual model simulation at Powder Patch in Juneau using snowpack. And this one I think is with her data, but the point is just that we can get this resolution of information in the snowpack, and it's not just liquid water content. We also can get things like snow temperature, which you can see, for example, there was like a really cold time here. I think it's in February, in February of 2025. And in general, though, in Juneau, we have a maritime snowpack that goes isothermal quite quickly. So actually, there's a lot of times where the snowpack is 0, and that's quite true. We were out this weekend, and there's a temperature gradient on the top, but the bottom of the snowpack went quite to 0 fast. So something cool to note is that the snow temperature you can pull, for example, this is a model, say this dotted line on the right is the snow profile for that day. And it's just one way to say that, okay, we have this snow model over time, but we can also do validation of the snow with the snow pit profiles on the right. And we can validate snow temperature, density, stratigraphy, grain type, whatever data we did collect and we have. But I mean, of course, ideally we're validating snow depth and snow density, which will give us SWE, like how much snow water equivalent is in the snowpack, which is what we're really interested in as far as if we're interested in for hydrology, if we're interested for flood forecasting, really the liquid water in the snowpack is what's quite useful. You can get other things as well from the model, such as grain size, which you can see like some layers that develop throughout the season. This is modeled at the same site. Snow density, this is like 200 kilograms per meter cubed up here, and then you're down to like 400 and 500. And yeah, from our snow pit profiles, the modeling is pretty spot on for snow density and SWE. It's quite impressive. It's physically based, so it's really going through all the physical processes and capturing the complexity of the snowpack. You can get grain type, which you can see that you kind of end up with all this melt freeze rounds because it's a maritime snowpack and you go isothermal, but there is some complexity in the grain type up higher in the snowpack. And then I showed you guys liquid water content already. So yeah, this is a really interesting, I think I show another plot, but this is really interesting because, I mean, this shows how the maritime snowpack like continuously will just be full liquid water flow through the snowpack. You have isothermal events, and then it will like switch back to a cold snowpack and then go back. So you have all these times that the snowpack is kind of going through this cycle. This is on the top is the example where I showed you forced only with her AK data, for example. So the top is only forced with her, and then the bottom is forced with Met Station data when available, and then the rest is with her. And I just put this dashed red line there to show like kind of this melt out period where just to show kind of there's a large difference in the amount of liquid water in the snowpack between the two simulations, primarily because the one simulation just accumulated way more snow. I think the one promising thing here is that because it's a physically based model, there's not much difference physically in the model for the whole season. The liquid water kind of melts out the same. Really what we're struggling with in modeling is the difference in snow accumulation, getting the accumulation right, and then getting the melt out timing right. Because once we can get the timing right, if we have the correct amount of snow, I think the physically based model will really kind of recover itself. So this is the details of what we're looking at with forcing data right now before we move somewhere where we don't have a lot of forcing data. So we really want to like validate this now, see the potential problems now in areas where we have data, and then we can go say, okay, we know these things exist, we know there's these potential problems, and then we can go model on the ice field where we don't have snow depth all year, or we don't have, we can move to places with less data. And I'll just show this again to say that, all of this was modeling on soil in a seasonal snowpack, but there are certainly ways to set up this model over glaciers, for example. There's one potential way where you can turn off the parameterizations for the communication between the energy exchange with the soil and the snowpack, and there's other ways to set you can set a base temperature for the bottom of the seasonal snowpack, and make sure that that's not at zero and it's at some negative temperature. So, I mean, there are many ways that people have done to set up a physically based snow model to model the snowpack on top of glacier. It's just a different setup than what I'm showing here. So that's kind of where we're moving to. And I think one of the things we're getting at is that we need to have high resolution forcing data. We need to be able to validate it, particularly precipitation. And then we also need model validation data at the points that we're modeling. So understanding how deep is the seasonal snowpack where we really are, and how much liquid water is really in that snowpack, and can we validate that? So, okay, I think that's all I have for now, but I'm happy to go back and share more. I didn't want to take up too much time of your workshop. So thanks for listening.
Questions for fans? Hey Cassie, it's Chris Gerby. Can you just say a little bit more about what the steps you think are between the point measurements and getting to that gridded data? I mean, I know that there's a long timeline between those two, but what are the steps and roadblocks between them right now?
Yeah. So then thanks, Chris. So yeah, right now what I showed was those point simulations, of course, which are really at this like fine resolution, daily temporal, like looking at these snow profiles. But yeah, going spatially, if we want to do spatially distributed simulations, I think there's a few steps. I mean, there's downscaling, which we feel pretty good about downscaling with air temperature and with wind speed. There's a lot of uncertainty with precipitation, and I think that like from what I saw in not to give people a headache, but like what I saw here, for example, is that really the only difference between the forcing data was air temperature, precipitation, and relative humidity. And the difference in just precipitation and air temperature alone gave like this order of magnitude difference in the timing, the amount of snowpack, and the timing of the timing of snow melt and ablation. So I know that there's a lot of uncertainty with downscaling precipitation, particularly temperature is a little bit simpler, lapse rate, some cold air pooling, but yeah, precipitation downscaling is certainly is a limiting not factor, but a more uncertain piece of the distributed modeling. So that when we're looking at this, for example, and we are trying to do some, distributed larger scale modeling, we really need to make sure that we are resolving the downscaling of precipitation and just making sure that we can validate it somewhere after we downscale it, which is really hard. I think there's some papers that have developed downscaling schemes over the Juneau ice field, particularly for precipitation. So that's kind of where we need to go for distributed scale.
Great, thanks.
Yeah.
Cassie, oh yeah, go ahead, Billy.
Thanks. This is super cool. Thanks, Seth, too, for passing it to me. But I guess I was wondering, the work you're doing seems really, really cool, really high value. And you have a specific like target in mind, it seems like, with the different sites you pointed out. But like, I guess I'm wondering for you, is the incremental difficulty of running it over a larger domain, like, is it something where you could do something that requires a little more computational time for you to run over a larger spatial scale, but then could make a data set that like runs over the whole ice field that could be useful to like a really wide group of people. Have you thought about that as like I guess I would be super interested in like using potential data outputs. Um, but maybe some of my areas of interest would be like a little further afield, further north than where it seemed like a lot of your targets were, and I guess further west as well. So like,
Yeah. So which like you mean more like you mean further afield as in on the ice field. You want like you're like, okay, hand me a distributed seasonal snow depth map over the ice field.
exactly. Is I mean,
Yeah.
like once you're running, like it seems like I imagine a lot of the hard part is getting the architecture right, and
Yeah.
then like increasing spatial scale is a time processing time thing. Is that true, or is it
Yeah.
complicated?
No, that's true. I think what you're saying is exactly right. The setup is so much the architecture, the setup is so much of the work. And if it's set up, then it's more like, okay, here it is, throw it on a supercomputer and look 5 days later and see your output. Um, so in short, it's totally possible and to do go that scale. I'd be curious like what resolution simulations are interesting to you spatially. Because like if you're talking like I think that is going to make a huge impact on how long it would take to run, for example. And then also the biggest thing is just like, okay, I hand you a snow depth data set that's model output, but like we don't know any validation of this thing, right? Like it's like if you're like if I am at this scale, and this is totally possible and we can do this, and but my biggest things are just thinking, okay, at this scale, if we're already off by like a month of of snow melt just based on changing like precipitation by very small. I don't think I have the forcing data here, but for example, the differences in the forcing for precipitation was super small, and you end up with this big difference. So my point is we get a map, we look at it, we're like, cool, this is distributed snow depth over the ice field for the seasonal snowpack. But how do we validate that? How do we? Maybe we don't, we don't know maybe how to trust that.
I mean, the what's it called? There's that mod scag thing, right? Like a MODIS derived snow covered area product where I think essentially like they track snow lines over time as a chat. Like so they do a PDD, a positive degree day model, melt model to say how much melt should be happening. And they can use tracking the snow line as a way of saying like we know this much melt occurred. If our snow depth is right, we should be able to see the snow line moving in this way. Like maybe something like that could help
That's
be a model constraint.
that's an interesting.
Um,
I really like that idea of like then you're looking at a spatial scale, and we say we take this period over a spatial scale over like May, June, July, August, and we look at the snow depth cover area, not necessarily even trying to validate snow depth directly, but the seasonal snow cover area, and we can compare it against something like that just to get an idea of our timing of snow ablation.
yeah, it's an
Yeah,
idea, I guess.
that's an idea. I like that
Yeah,
idea.
I hear your
So
point maybe about like if it gives you an unrealistic sense of certainty about what's going on, then maybe it's better to have no data than data with uncertain accuracy that you're treating as truth.
I
Um,
think that that's the point is that it's more like the conversation of just we're not treating this as truth, we're treating it as extremely experimental perhaps and seeing how what the application of it is. But I think what you're kind of getting at is that it is totally possible. And that's not very I don't think we're very far away from having some sort of output. And then my question mark is like how the heck can we validate it? So
So Cassie, I chime in on that too, because I think this is a good example of the value of the ice field. I'm only aware of one place that has, a dozen, uh, 4 to 7 meter deep snow pits dug, across a, 1,000 square kilometer area in North America, and that's the ice field every summer. And it's a function of having, 32 students there to dig these snow pits. And then the USGS compiles that data via Chris McNeil's work. And that's effectively what they do is these pits are dug during the summer. So Chris effectively models what the likely melt was to kind of back calculate how much snow had likely fallen at those sites. You know, and I think this is something that is always a sticking point when I think about trying to come up with a reasonable estimate of snowfall in some of these mountain areas that are getting like, 10 meters of snow, snow depth, right? Not really even accounting for the SWE and the density, but these areas that have massive snow accumulations that we don't really have any instrumentation in those locations. So that's effectively what the USGS has been doing, relying on JERP to provide these snow thickness measurements and density measurements in situ every season that we're there, and then modeling from that information back to the onset of melt. So I think that from my perspective, that's probably the first thing to tackle that Billy suggested. And one of the things that we're trying to do is install a better suite of sensors across the ice field. And I think there's opportunities to kind of think about sensors and systems that might capture these observations. Are there better ways to use SNOTEL sites in the area? There are better ways to kind of capture this information across that higher elevation area where you talk about 3 meters of snow, we're talking about 10 meters of snow. So what else can we do that can kind of cover that in these areas? I think is important for us to consider.
Yeah, I think that's a great point about that's totally, I also am not maybe necessarily the most aware of how much data you guys actually have on the ice field. So that these types of conversations I think are really valuable. And I think that, yeah, for the snow pits that that the students are digging on the ice field, I mean, that is certainly something where we can do point simulation comparisons and actually quantify it like SWE at those snow pits if they're taking density. And then for a larger scale, quantifying, snow cover area, snow melt timing. I think, there's enough data to do that level of validation. I think that's very interesting and something we should definitely do.
Many hands make light work.
It's great to have many hands. I was already like throwing out my back with a 3-meter pit. So your students deserve an award for their 10-meter pits. I need some photos of those pits actually.
All right. Thank you so much, Cassie. That was great.
Yeah, absolutely. Thanks for having me. And feel free to, anyone can follow up, I guess. On this, I'll talk to Chris and Seth and, and Emma and some other folks about this, but I'm happy to chat with anybody about this work and I'll be working on it, I think for a while now. So we'll get some distributed simulations over the ice field and do some comparisons.